No. Okay. Now the next topic is the regularization. So L1, L1 and L2 regularization. So first we will be seeing with the L1 regularization. Okay. So what is L1 regularization and L2? So these are nothing but the regularization techniques, okay, of the neural network. So, so if you have, if you suspect that neural network is overfitting, okay, then we can say that the overfitting the data means it is high variance. Okay, so one of the first thing we should try during this high variance or overfitting is nothing but the regularization. So regularization problem should be applied for this high variance. So for this, we will have to recall the logistic regression where min of w comma b, that is j of w comma b, cost of with respect to w and b is nothing but to minimize cost function j, to minimize cost function j. So j w comma b is nothing but equal to 1 by m summation I is equal to 1 to m loss function, that is y hat I comma yi. So a cost function is calculated with respect to the loss of the predicted output and the tagged output. Okay. Now here the cost is calculated with respect to the w. W is nothing but a rational number which is an n dimension vector. Okay, and b is nothing but the uh, normal rational or real number. Sorry, r is nothing but a real number. Now what we do is here we need to add this the loss function with the normalization function. So normalization is nothing is done usually with respect to the weights as well as biases. So the cost function, to reduce the cost function, uh, what we see is that we actually find out the loss function of that is applied to all the layers in the neural network. So that is nothing but summation of I is equal to 1 to m L of y hat I comma yi plus lambda by 2m w. Okay, this is nothing but norm of w squared. Okay, so this is nothing but your regularization of with respect to the weights. Okay, so here norm of w squared, which is nothing but summation of j is equal to 1 to nx, which is nothing but wj square, which is nothing but w transpose w. This particular part is called L2 regularization. Okay, because here we are using the Euclidean norm with the parameter w. Okay, a Euclidean norm with parameter w is used. Now why w? Why not b? Okay, why W is used, why not B? So like W, we can also use for B, that is lambda 2m B square. Okay, we can do this, but this can be omitted because this not because this W which we choose is a high dimensional, okay, parameter vector. Okay, that is W belongs to R to the power of nx, whereas B is just R. Okay, so it is a one parameter out of very large parameter. This L2 regular is common regularization for only W. Okay, now instead of L2, okay, we can add L1 regularization. So what is an L1 regularization? So if it is lambda by m summation of I is equal to 1 nx W, okay, lambda of m, okay, which is nothing but L1 norm of parameter vector W. Okay, so we can put, okay, instead of now you can lambda, we can also put it as lambda of 2m instead. Here also we can put it as lambda 2m here. Okay, lambda by 2m summation is equal to 1 nx, okay, W. Okay, instead of sum of square, instead of squares, okay, we are just using our norm of square, we are using only single parameter. Okay, so this is nothing but here, okay, a scaling constant. Okay, scaling constant. If we use L1 regularization, then we'll end W will be sparse. So if we use L1 regularization, then we will end W. Okay, then we will end W will be sparse, that is W vector will have lot of zeros in it, that is, okay, known as lambda. That is what it is having lot of zeros in it. Okay, and lambda here is called, which you can see here, is nothing but the lambda here is nothing but the regularization parameter, which is nothing but hyperparameter that needs to be set. And even in Python also we are using the lambda. Okay, now in the neural network, okay, we have all cost function of all parameters, that is nothing but W1, okay, B1, W2, B2, okay, up till WL, BL. Okay, now J of WL and so W1, B1 and WL, BL is nothing but equal to 1 by M summation of, okay, I is equal to 1 to M L Y hat I comma yi. Okay, plus lambda by 2m summation of L is equal to 1 to m W of L whole square. Okay. So what is this? This is the cost of the function, the cost of the function of all the weights and biases that are added is nothing but equal to 1 by m, that is mean of the losses, plus the L2 regularization. Okay, where this W L, that is L2 regularization, that is sum of squared, is nothing but the summation of I is equal to 1 to n summation of j. So I am talking about this particular thing which I was talking about. So this WL square is nothing but summation of I is equal to 1 to n summation of j is equal to 1 to n L minus 1 W of L I comma j whole square, which is nothing but a number of units. This is nothing but number of units in the corresponding layer. That is L and L minus 1. This particular aspect is known as the Frobenius norm. Frobenius norm. Okay. And now, how to implement this in gradient descent? How to implement in gradient descent? So, this can be done by change in the weights. So, in gradient descent means we are actually changing the weights is nothing but equal to from back propagation, whatever the change in the weights that is being done, that is nothing but dj by dw of L plus lambda by m w of L. Okay, so this is what we will be doing. I am giving this equation as one. Now this is my regularization of weights. Okay, so w of L is nothing but, now in gradient descent, w of L is nothing but w of L minus alpha dwl. Now what is w of L? That is the current weight is equal to previous initial weights minus the learning rate and the change in the weight. Okay, change in the weight is dw. Now this is nothing but your, now this dw is nothing but, dw of L is nothing but dj by dw of L. So but in Python programming or in programming languages, the mathematical notation of dj by dw is denoted by dwl. Okay, now this L2 regularization is also called weight decay. That is, we are reducing the weights. That is, we are penalizing the weights. Okay. Now, the equation which you can see here, okay, I had given it as 1. Now, implement this, okay, equation 1 in the gradient descent. So, what is the equation? That is nothing but this gradient descent is 2. Okay. Now, after I implement that, so I'll get it as W of L is nothing but W of L minus alpha, okay, from back propagation plus lambda by m w of L, okay, which is nothing but w of L minus lambda, okay, alpha by m w of L minus alpha from back prop, which is nothing but equal to 1 minus alpha w of L, okay, so 1 minus alpha lambda of m, okay, wl minus alpha from back prop, okay. Now this particular value should be less than 1, okay, should be less than 1, okay. This is actually how we are implementing the L2 regularization in the gradient descent, okay. Okay, so thank you. So we'll go to the next topic, okay, where we are using the regularization by using the dropping the nodes. Thank you.